So let's recap. A team at Lawrence Livermore National Lab, National Ignition Facility made the following happen. There's a tiny cylinder here at the end of this that you probably can't see. It's about so tall and this wide. Inside that was a small spherical capsule about half the diameter of a BB. 192 laser beams entered from the two ends of the cylinder and struck the inner wall. They didn't strike the capsule, they struck the inner wall of this cylinder and deposited energy, and that happened in less time than it takes light to move 10 feet. So it's kind of fast. X-rays from the wall impinged on the spherical capsule. Fusion fuel in the capsule got squeezed. Fusion reactions started. This had all happened before, 100 times before. But last week, for the first time, they designed this experiment so that the fusion fuel stayed hot enough, dense enough, and round enough for long enough that it ignited. And it produced more energies than the lasers had deposited. About 2 megajoules in, about 3 megajoules out, a gain of 1.5. The energy production took less time than it takes light to travel 1 inch. Kind of fast. So this is pretty cool. I have a special message to listeners who want to work on exciting, challenging, and important problems. We're hiring. So, fusion is an essential process in modern nuclear weapons, and fusion also has the potential for abundant clean energy. As you have heard, and we'll hear more, the breakthrough at NIF does have ramifications for clean energy. More immediately, this achievement will advance our national security in at least 3 ways. First, it will lead to laboratory experiments that help NNSA defense programs continue to maintain confidence in our deterrent without nuclear explosive testing. Second, it underpins the credibility of our deterrent by demonstrating world-leading expertise in weapons-relevant technologies. That is, we know what we're doing. Third, continuing to assure our allies that we know what we're doing and continuing to avoid testing will advance our non-proliferation goals, also increasing our national security. The achievement we celebrate today illustrates that big, important accomplishments often take longer and require more effort than originally thought, and that these accomplishments are often more than worth that time and effort that they took.
The face of society would be altered if we as a civilization were able to create a nuclear fusion power plant at a low cost. Every nation on the planet will be able to reap the benefits of this technology thanks to safe, clean fuels, allowing nations all over the world to be energy independent and avoiding one of the most common causes of conflict all over the world as we fight for control of energy sources. Every sci-fi utopian society is built on a foundation of cheap, abundant, and dependable energy. It would resolve our climate change issues, allow us to electrify steel smelting and other fossil fuel-intensive industries, allow us to establish brand new industries like water desalination that have been hampered by rising energy costs, supplying the entire world with clean, fresh water for irrigating our land and transforming arid wastelands into productive pastures, bringing about a new era of abundance that is clean and safe, a utopian future that has been envisioned for decades. Experiments in nuclear fusion have been going on since the beginning of the Cold War, with the first generators being turned on in the 1950s in both the United States and the Soviet Union. The Soviet Union used a tokamak design to solve the problem, while the Americans used the Stellarator, which was slightly different. The same issue is attempted to be solved by each design. Fundamentally, fusion is not particularly challenging. By combining smaller elements, we can create new elements and release a lot of energy. However, we must overcome the electromagnetic repulsion that separates the elements in order to successfully combine them. Atoms will repel one another, just like if 2 north poles of a magnet are pushed together. We need to put in a lot of energy to bring them together, but we can't just grab individual atoms and pull them together like magnets. Instead, we make a plasma, which is basically a cloud of changed ions that can be manipulated by a magnetic field because of their charge. The plasma can then be constrained within a magnetic field, preventing the ions from striking the walls of the fusion generator, and its temperature can gradually rise to extremely high temperatures, which would otherwise melt every solid substance in the universe. Ions move at a faster and faster rate as plasma temperature rises, raising the particles' dynamic energy so high that their speed alone permits them to punch through the electromagnetic aversion and impact. To achieve fusion, the tokamak and stellator designs employ slightly distinct methods of massive superconducting magnet-generated magnetic field confinement. In 1968, information about the tokamak design that showed a significant increase in energy efficiency was made public by the USSR, and as a result, the tokamak became the most popular design today. However, the fuels used in both designs were identical. The exact reactants we use have a significant impact on the amount of energy we need to put in and the final product. The majority of reactions use two hydrogen isotopes. One proton and one electron are in orbit in the nucleus of typical hydrogen. This kind of hydrogen could be used for fusion, but the amount of energy we could get out of the reaction is very little. Rather, we habitually consolidate deuterium and tritium together. Deuterium has one proton, one electron, and one neutron, whereas tritium has two neutrons and one proton, while hydrogen typically only has one proton, one electron, and no neutrons. There are a few uses for this combination. First, it is most likely to provide us with the desired outcome. Other reactions, such as a regular hydrogen-to-hydrogen reaction, have a very high probability of producing helium-2, which is unstable, rapidly decomposes into two regular hydrogens once more, and produces very little energy. Their likelihood of combining to produce the desired reaction, deuterium, is lower, which then, at that point, proceed to circuit to frame helium-3, lastly helium-4. This is the chain of reactions that drives the sun, but the sun has an unimaginable number of particles, so the question of probability is irrelevant, as is the crushing gravity that creates the conditions for fusion. If we can't extract more energy than we put in, that's just a science experiment and not an energy source. We need to supply those particles and the energy needed to combine them ourselves. On Earth, we have successfully produced a great number of fusion reactions. In fact, when I recently went to Helion, I was there and saw the fiery pink flashes of fusion for myself. Fusion is something we are skilled at. Increasing the amount of energy we can extract while decreasing the amount of energy we need to input is the issue we are currently attempting to resolve. Therefore, for step 1, we require fuels that consume less energy but produce more energy. Deuterium and tritium enter the equation here. They are very likely to produce helium-4 when combined, releasing 17.6 MeV (MeV) on average for each fusion event. Compared to uranium-235, the mass-based deuterium-tritium fusion reaction releases over 4 times as much energy as uranium fission does without producing any harmful radioactive products and produces approximately 11.4 times as much energy for each fission event, 200 MeV. Helium is actually a very useful byproduct. It is used to cool the superconducting magnets in MRI machines, to prevent rocket tanks from exploding after their propellant has been used, and occasionally to make your voice sound like it did in Wendover Productions 6 years ago. Additionally, since we will eventually run out of gas, having a means to make our own would be a nice backup. Deuterium is genuinely normal on the planet, happening normally in seawater, accounting for roughly 0.02% of the hydrogen in seawater. Deuterium's name comes from the fact that it makes that water molecule heavier because it has an additional neutron. A lot of water. We can differentiate it in a variety of ways thanks to this difference. The Girdler sulfide process separates heavy water through chemical reactions, whereas vacuum distillation allows us to take advantage of heavy water's higher boiling point. After that, we can easily electrolyze the heavy water to separate the deuterium. However, the scarcity of tritium is one of the problems with nuclear fusion. The moderator pools of nuclear reactors, which frequently contain a lot of heavy water, are our main source of tritium. Tritium can be produced by absorbing the high-energy neutrons that are released during nuclear fission into these pools. A 2-neutron hydrogen. As nuclear power plants around the world are gradually being shut down, this source of tritium is becoming less and less common,